Hello Sui, I'm Theo, and today I will talk about the concept of using a regular smartphone app to enable rich spatial inputs. I want to show that the tracking capabilities of modern off-the-shelf smartphones can allow easy-to-use, accurate spatial interactions, which can commonly only be enabled by expensive motion tracking hardware. I will present the implementation of our mobile app, a study where we validate its performance, and finally a few applications. Our motivations were external motion trackers that often come with VR systems and which allow us to track the position and rotation of the user's handheld controllers or bare hands in 6 degrees of freedom. Such systems allow us to perform powerful and already well-known interactions such as raycasting in VR, for example, or 3D object manipulation by grab, move, release principles that we all know from real-world interactions with real physical objects. Independently, if we use bare hands, a controller, a wearable headset, or control a distant screen at our home, office, or car, we can notice that our spatial interaction possibilities heavily depend on the tracking hardware which is surrounding us or which we are wearing. But what is when we don't have external trackers due to lack of infrastructure or cost, or when using external tracking is not possible due to energy requirements or computational power, or when external or wearable trackers are just not preferred due to tracking range limitations or public acceptance of the device? In such cases, our input possibilities are drastically reduced, and we would need a different input device for that. A great option is using the most convenient and available end-user device, the user's own smartphone. Related projects have shown that using a spatially aware smartphone can be a powerful alternative for 2D and 3D interactions. However, this research project still so far relied on using external tracking cameras, printed visual markers, or limited their interaction techniques so that they used only the phone's orientation detection rather than allowing full 6 degrees of freedom input. As such, we wanted to explore how we can use the tracking capabilities of 2018 smartphones. We wanted to develop just a single smartphone app which users can download over the App Store and put it into their pocket. And the objective of our app was to allow spontaneous use of it, so where we could just take out our phone, open the app, and it would work without any calibration procedures. It should also allow 6 degrees of freedom input, relying on phone's orientation, but especially also on its translation combined with touch. And it should provide enough tracking precision to allow subtle gestures, so that we don't need to perform large hand motions, which can be fatiguing, can be socially conspicuous, or cannot be performed in places with less physical space. And finally, our app should allow flexibility regarding body pose. So it should work while we are standing, sitting, or once we are in a public crowd with our hands down. We approached the implementation of the Pocket6 app by using an iPhone X and ARKit, that's Apple's augmented reality tool. But similar could also be achieved for Android system by Google's ARCore or Vuforia. The first goal was to enable 6DoF tracking of the phone. The phone's position and rotation in real-world coordinates is indirectly already available in ARKit. It's the position and rotation of the AR camera which we manipulate while we move around and observe all virtual objects which we created with our regular AR apps. If we read that out, we basically get a 6DoF handheld controller with a touchpad in real-world metric units. Since Pocket6 was meant to be only an input application which we can control, by which we can control a remote screen over Wi-Fi, we needed to define a control rate relation between the phone and the pointer on the screen. And we did that by using a virtual control space which was created as soon as the user opened the app. And the boundaries of this control space then enclosed the user's hand or the phone. And based on that, we could calculate the delta between the position and the orientation of the phone and the virtual space, which was anchored in real world by AR. To define this control space, the size of the control space, we performed a short pre-study which shows that user can easily manipulate a cursor where 1 centimeter of phone translations reflected into 120 pixels of cursor movement on the remote screen. As you will see later in the study and implications, we use the Full HD 16:9 TV as a remote screen, which hereby was mapped to a control space of a size of 16 by 9 centimeters, and for the depth we also used 16 centimeters. But to get a better impression on that size, it's pretty accurately almost the half of the regular man's shoebox. So you can keep this in mind, since this is the subtle space where all interactions seen later in the study and in the applications happened. At that point, we could open the app and interact already, but we wanted to give the user more movement flexibility to improve our objective on the spontaneous use. To do so, we implemented an automatic calibration algorithm, which was recalibrating the control space whenever the user changes the body posture or the orientation. The algorithm was basically checking whenever the phone's position exceeded the boundaries of the control space, and at that point, the recalibration was triggered. So this enabled us that we can freely walk to different positions with the phone. We can rotate our body. We can sit down, or we can even interact with our hands down, as seen in the video now. While the control space is always following us and keeps us correctly mapped to the output application at all times. So in this video, the user is also not doing any other interactions besides just holding the phone, and he gets a different kind of mapping. So that the implementation of the mapping was also the last step of the implementation. In cases where the user was standing or sitting, the XYZ of the control space was naturally mapped to the XYZ of the remote app. But since we had a hands down technique also, we needed to adapt the access of the control space accordingly. And this also occurred automatically once an upside down orientation of the phone was detected. Finally, we added the €1 filter to minimize jitter. And beside that, we didn't use any other signal processing here. After the implementation, we performed 3 experiments to explore the performance and benefits of the app-based approach. In the first 2D tracking experiment or task, we evaluated how accurately participants can continuously guide their hands through midair. In the second 2D pointing task, we investigated 2D pointing and clicking performance. And in the third 3D placement task, we performed a 3D object dragging interaction. To perform the task, we had 3 techniques: in front, sitting, and hands down, and the baseline. The first 3 were techniques using Pocket6 and differentiating just in the user's posture. And for the baseline technique, we used the state-of-the-art Microsoft Mixed Reality headset with its handheld controllers. In a routine subject design of our 12 participants performed all 3 tasks using all 4 techniques. So in the 2D tracking task, participants had to follow with the white cursor a moving target alongside an H-shaped path indicated by this red circle. And here you can see now the task and all 4 conditions, how they looked. And while participants performed their trials, we logged the distance between the target and the cursor. In this figure, we can now see the cursor traces of all participants and all trials. We see that the Pocket6 conditions, in front and sitting, allowed participants to perform hand motion as precisely as the baseline externally tracked controller. However, we found a significant difference between the 4 techniques, where the hand-down technique was more inaccurate compared to all other, on average for 16 to 21 pixels. The second experiment was a standard 2D fit slot task. And now we can see the task, but also how the user taps on the phone's touchscreen or touchpad on the controller to perform a click. Our test showed that hands-down technique had a significantly lower throughput, on average for 26% compared to all others, which throughput insignificantly differed only for less than 2%. Similar goes also for the error rate, where the hand-down technique had a higher error rate compared to all other techniques, which again did not differ that much between each other. In terms of movement time, the pattern again repeats, where only the hand-down technique had a significantly higher movement time compared to all others. From this result, we can see that Pocket6 techniques in front and sitting allowed users an equal 2D pointing and clicking performance in speed as well as in accuracy as an external track controller, while the hand-down technique, on the other hand, performed slower and more inaccurate. In the third experiment, we evaluated 3D interactions using a placement tasks, only translations. Participants faced two squares displayed on a remote screen. The two squares then had to be aligned by a 3D drag and drop gesture. And participants could resize the dragged square by removing their smartphone on the z-axis of the control space. When the two squares got correctly aligned, they both turned green. In case of a negative match, participants had to keep realigning, affecting the completion time. When the alignment was successful, both squares disappeared, and the participants needed to move back the 3D cursor to the screen center to get the new trial. Here is the task, and we can also see that we toggled between different positions and sizes of the squares. And as seen in this figure, all Pocket6 techniques, including now the hand-down technique, perform comparable to an externally tracked controller or baseline, and no significant difference was found here between all four of the techniques. After all tasks, we asked participants for subjective feedback by an exit questionnaire and interview. The focus was here to expose differences between our techniques based on their reactions and comments. So each participant rated each technique on a 7-point Likert scale for ease of use and fatigue, for speed and precision, and the general impression. In-depth analysis showed that no significant difference was found between the baseline, in front, and the sitting techniques in any of the categories. However, there was a significant difference for the hand-down and all other techniques in all categories. In their interviews, participants explained that Pocket6 works surprisingly well. It's fast, accurate, and easy to use. They said that the controller has a better ergonomics than the iPhone X, for example, and that it's therefore seems heavier, the phone. Although it's not the case, we checked and we measured the controller and the phone. They explained that sitting is comfortable. However, this is not always wanted. They explained that the armrest can be a serious limitation and an obstacle in case we need to interact in 3D, where we would need to move our elbow forward and backward on this armrest. The hand-down technique was the most fatiguing and the hardest one to use. They said that it's due to the long lever, the long kinematic chain from neck to the fingertips that need to be precisely adjusted. And they said that they could not interact like this probably for a long time. This was surprising, since we initially thought that the hand-down technique would be more relaxed and more comfortable due to the posture. And on the other side, they found that the mapping of the hand-down technique was good and understandable. So to summarize the study, we can say that the Pocket6 in-front and sitting techniques, with the exception of the hand-down technique, did not differ significantly in performance nor in the user's subjective preferences to the externally tracked controller. Now I would like to show you some applications that we did using our approach. So we can use Pocket6 quite immediately with a wide variety of real-world applications over the regular cursor interface. Now we can see an example where phone translations control the cursor, and combined with touch taps and swipes, we can perform clicking and scrolling. In the same manner, we could also then control a map, where you can do zooming into the cursor, zooming into Berlin, Oh, yeah. And we can also do 3D object grab, move, and release interactions, as in this cup pyramid game. We can see that the user grabs the objects by tapping down and holding, and by releasing, he releases the object. We can also combine phone translation with touch-based rotations, as seen in this interior designer app. By this we can simultaneously get to quite powerful 3D object manipulations. So some rearrangement. Yeah, so depth selection also interesting for spatial. And the last one is text selection, which is never easy if we don't have a mouse. So we were thinking also about that. And it also has some drag and drop of images. Yep. There are a few limitations of mobile AR approaches as Pocket6. When we are interacting, we need to watch out that the tracking doesn't stick to some moving objects or another person or a user that is standing in front of us, since as soon as this person moves, our tracking drifts away with him. And while we interact, we need to watch out that our fingers don't accidentally cover the phone's camera, since this also breaks the tracking. Although the ergonomics of larger smartphone was seen in our experiment as a minor problem, we suggest few simple add-on solutions which can easily improve the gripping experience by using an off-the-shelf elastic grip or ring grip, some magnets, or more advanced solutions as a personalized 3D printed case or a foldable foam bag which would turn into a controller-like handle once needed. To conclude, we present an inexpensive, accessible, and easy-to-use SIGCHI input controller in the form of a smartphone app called Pocket6. We present a simple and efficient auto-calibration algorithm which adapts the user's control space whenever they change their position, orientation, or posture. We showed that with Pocket6, users can do subtle hand gestures to achieve high-performing 2D and 3D interactions without any external hardware. We conducted a study where we validate its usability in 2D and 3D tasks, comparing between different body postures and a baseline. And finally, we showed some applications. In the future, we can imagine extending Pocket6 in multiple ways, by improving the phone's ergonomics, providing phone-enabled haptic and acoustic feedback, using touch pressure for 3D virtual grabbing, or investigate how to make it work while we would walk and not just stand. Thank you for your time, and now I would like to answer some of your questions.
Any questions?
Very nice. Did you consider comparing your technique with other hands-down methods to find out if the lower scores for hands-down were intrinsic to hands-down or to your version of hands-down?
Mm-hmm. So we didn't compare that. We, of course, the hand-down technique was also very inspired by related works that did hands-down interaction, but also often hands-free, basically, so there was no controller or device in the hand. But we didn't check it for different, let's say, versions of hands-down, so either if the user was holding his hand like this, or the other way around, I don't know. So we just set users hold however you would hold it without any special limitation, and usually all of them hold it like in a way like this, and this is how we then also evaluated the study. But if we would need to figure out, but since hands down has a concrete use case in public, no space, standing, and maybe also in combination with VR glasses, it would work, or AR glasses would work good. We would need to see what's the best hands down posture or how the device should be held. But we didn't do anything in the scope of Pocket6.
Hey.
Hey.
So I noticed two things that you didn't talk about, or really didn't show. One was sort of how fast you could move the device, and I also noticed that there was really no use of the phone orientation. Can you talk about sort of the performance boundaries, and maybe they're related, those two questions?
So it was a subtle control space. So for example, in the fit slot tasks and in also the others, the users were trying to get faster as fast as possible and not to overshoot. And maybe this was not that much visible, since a couple of centimeters here already reflect to like half a meter movement on the screen. And if we have in mind big gestures, this would be much more obvious. And we focused, it's true that we focused heavily on translations and touch and not that much on rotating the phone, since this was also the hard thing to get. So orientation, there are a lot of works using phone rotations already, but the translation of the phone is really, this absolute is really something that is special about Pocket6. And this is why we set the focus to a bit more to the translation, and also how we use external VR controllers. We don't really rotate the controller that much, although we see VR apps, they grab the controller and then they still use the touchpad to rotate, or maybe the joystick to do some manipulation. So we would need to think about that. But what we know is, since we tested it, is also that rotating the phone, for example, with the tracking, basically the cloud points that are placed on the ground would then go somehow up due to the camera rotation. This still is stable, so ARKit manages that really well, so it probably won't lose tracking that quick.
Thank you.
No problem.
Thank you. Jan Borges from Aachen. I really liked your implementation of this. This looks really like you could use a smartphone to do this kind of control. The thing that you briefly mentioned, and I'd love to hear more about, was the recalibration process, because that looked like that was the moment when the interaction kind of broke, if you like, if you left your control box. And then I noticed it looked like you were recalibrating and just sort of jumping the cursor back into the center of the screen.
Yep.
Can you talk about the motivation for you making that design decision, alternatives you considered, user feedback on that? Did you test that maybe? Thanks.
So I can replay this video where this is basically where it's happening actively, and so and as seen on this picture here, this is actually what happens. So as soon as the phone gets out of this control space or leaves the anchored control space, it will start recalibrating. So it will put a control space after control space until we stop at certain point. So in that time we also shut off the cursor, so otherwise the cursor would basically just fly over the screen all the time. So we had some dwell mechanic in there, but this can also be avoided. So this is not really, this is just a visual thing, let's say. But otherwise it's literally just the difference between where the center of the control space is and the phone position. And as soon as this happens, the next control space gets anchored at the phone's position. So if you move down, the control spaces would go down. If you rotate, the control space will start rotating. And also with the hand down mechanic, where the control space basically flips or like mirrors its axis. And this is how it works. So eventually at the back end, it's really just this one if function, which was then seeing, okay, is the phone outside of the control space, do the remapping and do it correctly for the orientation or the hand posture.
Just jumping cursors always make me nervous.
Oh, yeah.
Continuity of
Yeah.
interaction. Just basically dragging the control space box along. If you leave the edge, wouldn't that give you a similar effect without the?
Yes, that would be the similar effect, but then the question is how you would automate it. So there you probably would need to maybe have a button or something that you say, okay, follow me or something, or map it now, then no cursor jumping would happen. But we wanted to have it just that you can walk without doing any inputs. And then we would need to maybe figure out a much more, let's say, a visually more stable dwelling or some other principle that would not cause the cursor to jitter.
Thank you.
Yeah.
We're actually a little ahead of schedule, so if you have any more questions.
Oh yeah.
There's some slight delay between the actual interaction and
Mhm.
what is visible in the screen. Do you know where it comes from, or do you have any assessment made that it's from the transmission or from the processing? Or?
Mm-hmm. So the processing was, we were making sure that the, let's say, processing pipeline was exactly the same for the app and for the controller. So because that would then obviously not be valid. So we had the one library which was taking out the controller inputs and the phone inputs, and then passed it to the applications. And the slight lag, then of course they both jitter a bit, so this is why we added the €1 filter. And then we just basically we set it so that it was fitting well to the tasks that we were trying to do, and that it was not lagging too much. So the lag is definitely there, of course it is. But we think that it's still manageable, and we could even push it down a bit, since we need to know that all those interactions, or in the study especially, are really the limit, right? So the smallest objects, the smallest distances, in real case we would not have on such a big screen maybe 4 pixel small cubes, right? So then it would be much easier to turn down the filtering and make it a bit faster, less latency, and yeah.
One of the more difficult things here would seem to be, if we're using for like a HoloLens or a virtual reality headset, aligning the two spaces. So you actually get sort of one-to-one
Yes.
motion with your hand. Have you looked at that at all? And how would you propose to do it?
Yeah, so good thing is that we can use something like Unity or something, right? So we can get, let's say, the information from the HoloLens and from the app into one coordinate space, let's say. Then we just need to figure out how to bring them together. And this approach would probably then be off in space. So we would need to somehow make it happen that the phone would be mapped to the HoloLens's space. And we could do that maybe also with the help of ARKit, since it has the image recognition feature, or 3D object recognition feature. So maybe we would then really need to have some external marker, or maybe even the HoloLens. I could point it, I don't know, or maybe to my shoes, whatever. And then we would do the click calibration, and then the phone would be in the HoloLens space. But doing it without any external calibration, and then it's a hard thing to do, probably. Not yet.
Okay, we should probably wrap up here. If you have any additional questions for Theo, you might catch him later during the break. Anyway, let's thank the speaker again.
Yeah. Thank you.
Could I have the next speaker for Haptopus come up, please? Takayuki, is that you? Oh.